Swayam Prabha. Digital India. Educated India.
Namaste. Today we will have a look at a technique known as LIDAR, light detection and ranging. So this week covers the ways of measuring the height of a tree. LIDAR is another method of measuring the height of a tree. So what is LIDAR? LIDAR is an active remote sensing technique. So now to divide this word into its parts, it is active remote sensing. What is remote sensing? Remote sensing is a technique in which you gather information about an object without getting into touch with the object. So as we did it before, if this is our object, if I am touching it, this is not remote sensing, but if I am seeing it from a distance and the light rays are interacting with this object and coming back to my eyes, and I am getting information about this object regarding its maybe its shape, its length and so on, that is a technique known as remote sensing, gathering information from a distance. So it is LIDAR is a remote sensing technique. It is also an active remote sensing technique. So remote sensing is divided into two parts. You have active and you have passive remote sensing. Now passive remote sensing is something that we are doing every day. So when we are using the energy of the sun or maybe the energy of the ambient light sources and we are trying to get information about something. So when I am looking at this pen, I am using the energy of the ambience and those light rays are getting reflected back to my eyes and I am getting information about this pen. So that is passive remote sensing. Active remote sensing on the other hand uses a technique in which you fire some sort of a radiation to your device. So suppose we had this pen here and suppose I threw some light sources. For instance, suppose I was throwing laser lights. Now those laser lights would then interact with this object and then be reflected back, and then I would measure them again. So that sort of a remote sensing in which we are using energy. So active uses energy, passive uses ambient energy or the sun's energy. Now LIDAR is an active remote sensing technique, which means that when you are using LIDAR you need an energy source to illuminate your object, and with that energy source the radiations that are coming out, they will interact with your object and then they will come back. Now coming to the slides again, it is a technique of airborne laser scanning. So it uses laser, it scans things using laser's energy. It can be used in an airborne fashion. So when we say an airborne fashion, what we mean is that suppose you have a plane, you can put your LIDAR device here and suppose it is going above the earth, it is getting some buildings, maybe a few trees. So now this laser light would be scanning the whole region in different ways that we will come to in this lecture, and it can be used in an airborne fashion. Now coming back to the slides, so it is this word LIDAR, it comes from laser plus radar. So radar technology was developed first, and then people thought about adding laser as the source of energy. Later on this term was also expanded to mean light detection and ranging, but the origin of this term is laser plus radar. It was developed in 1960 by Hughes Aircraft Incorporated. Now why should we use lasers? The use of laser is because of its two properties. One, it is monochromatic, and two, it is directional. By monochromatic we mean that the laser light will have a single wavelength. Now that single wavelength is completely known with the device. So, why do we need a single wavelength? So, suppose you have a tree and suppose you illuminate it with say red colored light. Now, leaves are green in color, which means that they reflect only the green portion of the spectrum. So, if you took a leaf into a dark room and if you illuminated it with red light, what would you see? You would see a black colored leaf. If you illuminated it with green colored light, you would see a green colored leaf. If you illuminated it with say blue colored light, you would again be seeing a black colored leaf, which is because different wavelengths interact with the same object in different manners. So, by using a monochromatic beam of light, we ensure that we have specific interactions with that wavelength. So, if suppose you wanted to measure the properties of some object at different wavelengths, you would be using different wavelengths or laser beams of different wavelengths one by one. The second use of laser is that it is directional. So, by directional what we mean is, suppose we consider a point source of light, suppose say a light bulb. So, its energy is going out in all directions. Now, at this point the intensity of the energy would be high as compared to this point. Why? Because this small portion of light that was coming here, it has diverged with distance, suppose at this point. So, here you are getting this cone of light, but at this point you are getting a very small, a tiny cone of light like this. So, the intensity at this point would be less than the intensity at that point. In the case of lasers, they are highly directional. So, basically their beams are exactly parallel to each other. So, even at very large distances you do not see any divergence, and so its strength remains large over long distances. So, what is the concept of using LIDAR? When we are using LIDAR, we need to get the position of the aircraft. Now, the position of the aircraft can be had using two systems. You can use a differential GPS or you can use an inertial measurement unit. Now, in the case of a differential GPS, we have a constellation of satellites moving above us. So, suppose this is the earth and we have a number of satellites for GPS that are going all around it. Now, if we want to know the position of this particular point, we can calculate its distances from a number of satellites. So, these satellites would be beaming energy from this point of the observer can be calculated by measuring the time difference this signal takes to reach this point. So, suppose it started at a time t0 and it reached here at time t1. So, the time of flight for this beam of energy, which is an electromagnetic radiation moving at the speed of light. So, the time of flight is t1 minus t0. Now, we know the speed of light c is equal to 299,792,458 meters per second. So, we can calculate this distance d as c times t1 minus t0. So, we can calculate this distance d. We can all similarly so suppose let us call it d1. We can also calculate distance from the other satellite, from another satellite, from another satellite, and so on. Now, when we have these measurements, if we can calculate, so considering this satellite, so we know that our point is at a distance of d4 from the satellite. So, when we say that, what we are getting is from this satellite it is at a distance of d4. So, we can draw a sphere all around it with a radius of d4. We know that our point is somewhere on this sphere. Now, using another satellite, taking the measurement from another satellite, we know that it is at a distance of d3. So, our point is at a distance of d4 from satellite 4 and at a distance of d3 from satellite 3. So, it would our point would lie in this circle that forms out of the intersection of these two spheres. Now, if we knew that R point is at a distance of say d2 from another satellite. So, we have another sphere of radius d2 and this sphere is going to cut our circle of position at 2 points. So, we would now know that our position is one out of these two. Now, if we took a fourth sphere, so we know that we are at a distance of d1 from the position of this satellite, satellite 1. So, we would now be able to say that out of these 2 points we are not at this point, but we are at this point. Now, we generally require only 3 spheres because the fourth sphere is the sphere of the earth. Now, this would give us our position. So, this thing is known as GPS, which stands for Global Positioning System. But there is a catch with GPS. These readings, it is based on the calculation of these distances. These distances are based on the calculation of times of flight. Now, it also depends on the exact position of the satellite. Now, we could have errors in all these measurements. We might not know exactly the position of that satellite, or maybe we do not exactly know the time of flight, or maybe there is some error in calculation. So, that would give us some difference or some margin of error. So, our point would not be a single point, but might be say a big circle. Now, to reduce that circle, if we wanted to know our position with a greater precision, what we would do is we would take 2 devices. So, we would have a GPS 1 that is kept at a fixed location, also known as a GCP, that stands for a ground control point. Now, we exactly know the position of this device. On our aeroplane, we would keep the second GPS. So, we have GPS 2, and whenever we are taking the readings, we are taking the readings from GPS 1 as well as GPS 2 at all times. So, suppose our reading of our position here had P plus delta P, and this one had Q plus delta Q. So, P and Q are the positions and delta refers to the error margin. So, suppose we had this P plus delta P and Q plus delta Q. Now, any if these 2 points are close by, then any delta P that is occurring here because of the positions of the satellite, because both these instruments are the same, the satellites are the same. So, this error would be the same in both the conditions. So, if we calculated the distance, the position of GPS 2 with respect to GPS 1, we would be getting Q plus delta Q minus P plus delta P. Now, because delta Q and delta P are the same, they would get cancelled out and we would exactly be getting Q minus P. Now, this use of these 2 instruments for calculating this difference is known as DGPS, which stands for differential GPS. Now, coming back to the slide, we need to know the position of the aircraft in very high precision. We can use it, we can use a differential GPS. At the same time, we also use an inertial measurement unit. Now, an inertial measurement unit can tell us any small deviations in its position. So, suppose we were using a laser beam, then if this aircraft tilted a bit, we would need that tilt as well. So, that is had with the inertial measurement unit. Now, what our aircraft is doing now is that it is flying overhead and then it is using a laser beam to scan things. So, suppose this were a ground. suppose we had a building here. So, when the laser beam comes here, so it comes and then it interacts with the surface and then it is reflected back. Here it interacts with the ground surface and it is reflected back. So, we can calculate this distance d1 and calculate the distance d2 as well. How do we calculate that distance? Again, because the speed of light is constant, it is c, we can get d. So, when this light is going from the aircraft to the ground, it is traveling a distance of d1. When it is moving back, it is again covering a distance of d1. So, we have twice of d1 is equal to c multiplied by the time of flight, which would give us that d1 is equal to c times say t1 c times t1 upon 2. Similarly, from this position for the position of the building, we can calculate d2 is equal to c times t2 upon 2. Now, if we exactly knew the position of our aircraft and its tilt on all the axes very precisely, then just by knowing these d1 and d2, we would be able to reconstruct the scene computationally. So, coming back to the slide again. So, by keeping track of the angles, we can get a 3D scan of the whole scene. So, what are the components of a LIDAR? It consists of a laser, it consists of scanner and optics. So, a scanner refers to the instrument that is used to move this beam, plus you will have some optics to ensure that your beam is a very coherent beam. Then once this beam has interacted with the surface and has moved back, then you will need photodetectors and receiver electronics. So, you have sent this beam, it has interacted, it has moved back, and now you need a photodetector here on the aircraft to sense that beam, and then you will require receiver electronics to convert that into a signal. Plus the fourth component is the position and navigational systems that we have already seen in the form of differential GPS and the IMU. So, this is how this scanning would look like. We could go for ground based scanning, so which would be called a ground LIDAR system. We could put it on an aircraft, say an aeroplane or a helicopter. We could even put it on a satellite, or you could put it anywhere essentially, but you need to know your position, you need to know all the angles, and you need to calculate the time of flight of the laser beams. Now, when we are moving the laser beam to scan our surface like this, so this scanning can be done in a number of ways. So, if we looked at the slide now, we can use an oscillating mirror. So, this mirror is going back and forth like this. So, in that case it would be giving a scan in this direction. So, it will move from here to here and then back, here and back, here and back. Now, remember that our aircraft is moving on a direction. So, essentially this would be making out angles on the ground. So, if we looked at the slide now, so this makes these angles. We could also be using a rotating polygon. So, in the case of a rotating polygon, consider this to be the polygon. So, now this polygon is rotating. So, when it is rotating, the beam is interacting with this surface, then it moves at an angle, then it moves at an angle, and then it goes back to 0 when it gets to the other surface. So, coming back to the slide, if we used a rotating polygon, we would be getting parallel lines, or we could also be using a nutating mirror, which would give us elliptical lines of scanning on the field. Now, LIDAR is divided into two families. One is called waveform LIDAR. So, in the case of a waveform LIDAR, you take its you measure the amount of energy that is reflected with the with this laser travel time. So, for instance, if in this figure we look that on the right we have a tree. Now, in this tree, when the laser light interacts with the canopy, it would come back with a higher energy. Then when it reaches to the bole portion, then most of the light from there does not come back, only that amount of light that interacts with the bole is able to come back. And then when it reaches to the ground, then again you will be getting a high signal. So, if we looked at our waveform, so what we will be getting here is that for this canopy we are getting a huge amount of signal. then for the bole we are getting a small amount of signal, then for the ground again we are getting a large amount of signal. So, this waveform LIDAR would give us the shape of the object. The other family is called as a discrete LIDAR. So, what a discrete LIDAR does is it does not measure your amount of energy that comes back, but it just measures the actual position from where this energy is coming back. So, if we did a discrete LIDAR, then it would get this point, it would get this point, and it would get this point. So, how it would look is, suppose we did it for a bridge. So, on the right we can see a bridge, on the left we are seeing a discrete LIDAR pattern. Now, what sort of wavelengths do we use in LIDAR? So, remember that it is a laser system and a laser beam has a fixed wavelength. So, what are the wavelengths that we use? There are a number of considerations here. One is that your beam should be able to interact with the object. So, essentially we use those wavelengths that can interact with the object. Two is the safety criterion. So, for instance, if you are putting a laser light on an aircraft and it is shooting it down to the earth, so if somebody is looking up onto the sky, or if somebody is intercepting that reflected laser beam, then his or her eyes should not get damaged. So, those are the two considerations. So, we deploy two kinds of wavelengths in LIDAR. In the case of topographic LIDAR that we use for ground surfaces, we use a near infrared laser to map the land. In the case of bathymetric LIDAR, that is used to get the surfaces of seabeds or maybe rivers or maybe lakes, then we use water penetrating green light. So, because green light does not interact with water, whereas red light would interact with water. So, if we are using a green laser, it would go right through the water, it would interact with the bottom surface, and then it would come back to give us the sea floor and the riverbed elevations. So, so far so good about LIDAR, but then what are the uses in forestry? Now, in the case of canopy measurements, so for instance, this is an old paper, it talks about how canopies overlap over each other. So, the circles or the dots that you can see are the stem boles, and then we are seeing the canopies. So, they interact with each other. So, if we actually wanted to know this physically, we could use a LIDAR. So, this is how a LIDAR would be used. So, here we are seeing DEM and canopy. Now, DEM stands for the digital elevation measurement. So, on this slide in this figure C, what we are seeing is the bare ground surface. So, we are using those wavelengths that either do not interact with the trees, or we are only using those radiations that are coming from the ground, and then we are patching up the gaps in between. Now, the other ones show us the canopy. So, we can use both of these to get a 3D scan of our tree. So, here we are seeing these trees. So, we are getting this 3D picture of the tree. We can also take a section from any of these, and this is how the sections would look like. So, this is the top section, it is smaller as compared to the central section, which is then again bigger than the other section, and then this D section, which stands for the bole, is a very small one. So, we are getting a 3D picture of the tree. Now, this 3D picture can be used to compute the leaf area density. So, in this graph we are seeing the leaf area density as computed from LIDAR and as computed physically from a tree. So, as we can see, there is a very good correlation between both of these. Now, if we have this 3D picture of a tree, we can also use it to compute the canopy height. So, in this case we are using all those radiations that are reflecting out from the tree tops, and then we are also using this digital elevation measurement to get the elevation of the ground, and so we can get the height of the canopies. We can also use it to get the carbon stalks. So, basically once you have a 3D model of your tree, you can multiply it with the density of various portions of the tree to compute the amount of mass that is there, and then you can multiply it with another factor to get the amount of carbon, say in kilograms per tree. Now all this information can be had from the airborne laser, but we can also use a horizontal LIDAR. So in the case of this horizontal LIDAR, these different colors are showing the distances from the LIDAR. So for instance, this tree is close by as compared to this tree. So here we have put our LIDAR out there on the ground, and that is scanning the whole forest region, and once it has scanned the whole region, it will give you this picture of the forest. We can also use that to measure the carbon stocks. Now LIDAR can also be used to understand plant growth and the shape change. So for instance, here in this picture we are seeing aubergine, which is of the brinjal family, and we are seeing a plant that has been modeled thrice using a LIDAR at 3 different points in its life. So when we are using this LIDAR system, we can exactly compute the volumes of the leaves, and for instance we can compute the amount of carbon that is there in the leaves, or we could also use it to predict to study the growth of this plant or how its shape changes with its age. We can also use LIDAR to understand forest growth. So for instance, in this figure on the top panel we are seeing a young plantation followed by a mature plantation followed by an old growth. So why do we get this image? So for instance, in a young plantation we would be seeing very thin trees that are close together. So this is a young plantation. Now later on we could put this plantation through thinning. So it could go through a thinning operation in which we remove some trees, so that any trees that are remaining are able to grow in their size. So after a while we will be getting trees that are much broader, but now their number is less. And then in the case of an old plantation, when it becomes very old, we would be seeing a few large size trees that are very much separated from each other. So now coming back to the slide, here we see that in the case of a young plantation, we are seeing that its boles, they are having very small diameter and they are having a good height and it is roughly continuous. In the case of a mature plantation, we are seeing that the bole diameter has increased. So essentially if you looked at this point, this is the diameter of this tree, whereas here this is the diameter of the larger tree. So its diameter has increased and it is still making a continuous canopy even in the mature case. In the case of an old growth, so here we are seeing that we have a tree here, we have a tree here, we have a tree here, we have a tree here and so on, but so much of the space is left in between these trees. So we are seeing some trees that are very much in diameter, but they are quite separated from each other. Now the next figure shows you a young plus a mixed plantation. So and the last panel shows you a mature plus mixed plantation. So essentially you can use your LIDAR information to get an idea of how your forest is at a particular point of time. You can use it to get the forest growth, or you can also use it to calculate the amount of biomass that is there in your forest in different stages. So LIDAR is one of the most groundbreaking technologies that we are using in the case of forestry today. Thank you for your attention. Jai Hind.